So I'm doing this problem for this presentation that let the v be in the complex number and a map by the v a plus bi is equal a minus bi. First, I have to prove that the v is a homomorphism. Over here, in order to do that, we need to know the definition of a homomorphism. It's preserve the operation of addition and multiplication. What does that mean? It's mean here phi bracket a plus b has to be equal phi bracket a plus phi bracket p, and for multiplication phi bracket a p is equal phi bracket a times phi bracket p. So that's what it means to preserve the operation of addition and multiplication. So next up, we're gonna use what we gave to check if it preserved the addition and multiplication. First, we're gonna need to have two value of complex number. We can use to a plus bi and c plus di, and for the addition we like this here. So we need to show that this is equal here. We can do this by like this, by just doing the addition here. We combine them by put together just the value and together the coefficient of I, and after that we apply the math by changing the imaginary number to negative, and we end up with this. Then we get this a minus bi plus z minus di, that's equal v to the phi a plus bi plus v plus bracket c plus di. That's mean that it preserved addition. Now we're gonna check if it's preserved multiplication. Here, like similarly, same thing. For multiplication, we need to show that the v, the two complex number a plus bi times c plus di is equal v a plus bi times v bracket c plus di. So the left hand side have to equal to right hand side. So for here we can do both sides to see if they're equal. So if we expand the right hand side first, we end up with a z minus bt minus a plus bci. And then if we expand the left hand side too, it's end up with the same answer, which is mean they are equal. Then that's mean this the phi preserved the operation of multiplication. So we can conclude that the phi is homomorphism. The next question, what is the kernel of phi? Definition of kernel of phi is equal to the R in the R set, where the phi times R is equal to 0. So everything that are sent to 0 are in the kernel set. So here in this problem that I'm doing, the kernel have to be equal to an integer in the complex number where that integer is sent to 0. Like phi a plus bi have to be equal if a minus bi have to equal 0. So we need to find what value of a and p can send to be 0, and then we can find out it's only 0 integer can send to 0. So the kernel of phi in this problem is 0. And for our last question, we have to show that is phi an isomorphism. So we have to show if in order to be isomorphism, we have to satisfy homomorphism, which we already proved that. And also we have to show it's one-to-one and onto. So here, let's first show it's one-to-one by using there the A plus IP and C plus DI in the complex number too. So we show it by equal, and we end up here. A is equal to C, B is equal to D, and A plus IP is equal to C plus DI. Then it's mean it's 1 to 1. But to us to prove if it's onto, we take a value of Z. If we do it, A minus BI is in the complex number. A plus IP is in the complex number too. Now we say here, and we expand it, then it's equal to A plus IP. So A minus IP is, then it means is onto. So it satisfies the 1 to 1 and onto. So it means that the phi is a isomorphism. Yeah, mahalo.